Cool. Go for it, Jamie.
All right, aquifer storage and recovery, specifically related to Horton Kirby. So here's the River Darent, and we all are very much aware of the issues that were really suffered in the 70s, 80s, the early 90s, which was the kind of starting point of the Darent Action Plan and my life at Thames so far. The River Darent starts up here in the lower Greensand areas, southwest of Westerham, receiving water from the lower Greensand, a few of the scarp springs that come out of the chalk, before it then gets to Sevenoaks and then heads north through the North Downs. We all know about that. We've got Westerham up here from the chalk. We've got Sundridge here. These are Thames Water's abstractions. Sundridge from the lower Greensand. Then as we flow through the north bit, we start with Lullingston. Then we've got Ainsford. Move on to Horton Kirby, and then further down we've got Darent, Wilmington, Dartford. So they're all our abstractions which are along the River Darent. We've got the other cray sources from Orpington, North Orpington, Bexley, Wanson, Crayford. And then as part of this programme, we're drying up rivers. We don't like that. We need to do something about it. So we set about developing this new chalk wellfield. The whole of that was intercepting groundwater flow, which was at the time flowing towards what was Eastern Quarry, an active chalk quarry. Some elements were still going to Western Quarry, which is the Blue Water shopping centre. Obviously, chalk quarrying stopped in 2008, but construction dewatering has continued since there. We developed all of these boreholes to intercept that water, did a lot of monitoring to ensure that any of this abstraction was not detected at the expense of the River Darent, because we didn't want to reduce abstraction here to improve flows to only then start the abstraction up here and cause reduced flows here. So as part of that license application, we both observed and modelled various abstraction scenarios that demonstrated that we weren't interfering with flows in the Darent. So we make these reductions, and that's all good, and we continue to do such things, but the population keeps growing and demand for water keeps going. We're all going to do our best to reduce per capita consumption, and we've still got that battle ahead. But the demands for water increase, but we want to be building on what Stuart said, building resources that are more climate change resilient. So this is where the context of our aquifer storage and recovery scheme is very much centred on the Horton Kirby site. This red line that's on here, just remember that is going to be my slice of geology that I'll show you in a bit. It just kind of shows from Sevenoaks to Horton Kirby what the geology underneath there would look like. Here's the very, very simple concept of ASR in particular. This is at the Horton Kirby site. So we've got an existing chalk borehole that's in here. We've got the chalk, which is this lump of pale green that's here. Then you have this clay horizon, which isolates this lower aquifer, which is the lower Greensand, which is really quite thin. You know, at Sundridge, at Sevenoaks, it might be 70 meters thick. At Horton Kirby, if we're being very positive, it's about 15 to 20 meters thick. In reality, it's probably about 10 meters thick. So it's quite thin, but it is a really nice beach sand. So it's got high storage capacity in there. So the concept is that during really wet spells, you've got lots of rainwater around, groundwater levels are healthy, then there's surplus to the system, still allowing for sufficient natural flooding that the rivers are going to require, but taking off any surplus above that, then that can be treated and injected down into the lower aquifer, where it sits as a bubble. That the aim is that it sits as a bubble that doesn't interact with the existing groundwater that's down there. Then it can store for a while, and you just leave it there, and it doesn't move away. It remains where you've put it. And then at a later time during drought conditions, this then enables you to take that water, undergo really quite limited treatment. So you only, if you have to treat it for significant water quality parameters, then it doesn't really stack up. If you can get away with just disinfecting again and then it's straight back into supply, then that works. So that is really the concept of ASR, and these are just words that I've just gone through. I think the bit that I'd like to emphasize is that climate change resilience. This enables these fluctuating heavy rain, high groundwater flooding events, where we can take that and do what is really the future of water resource management. It's all about storage. It's managing a similar amount of annual rainfall that comes in more extreme measures. So you're going to have more prolonged, longer droughts. You're going to have more intense, wetter periods. It's just going to be spaced out a bit. So that's what we hope is the real advantage of ASR. Just quickly running through Horton Kirby. So we started the investigation drilling the first borehole in 2005, I think it was. Really just to see whether the lower green sand was there, which thankfully it was, and we were able to abstract a certain amount of water. It's much less productive than the chalk, but it still enables us to get about 3 megalitres a day out of the one borehole, which meant that we then continued to drill a full-scale ASR borehole, which was done a year or so later, 2006-07, and then we equipped this with temporary recharge facilities that enabled us to then in 2008 carry out some cycle testing, which I'll describe what that is in a bit. Back at that stage, we envisaged that the Horton Kirby ASR scheme would be then developed by drilling additional boreholes, all within our land ownership at the Horton Kirby site. The information that we got really soon proved that wrong, because the interference effects, if you start putting all of this quantity of water down into this thin aquifer, means that your recharge pressures, i.e. where the recharge water level would come up to, would be astronomically high and would cause all sorts of issues with ground stability, etc. Hence, when we came back in 2012-13, the kind of distribution of the borehole separation was this kind of a kilometre, about 800 meters each, as a grid of a square is the original plan, which is when we moved on to drill an additional ASL borehole down near to Farningham, down again by the River Darent at the bottom there, such that the scheme we have now has an ASR borehole at Farningham, an ASR borehole at the Horton Kirby site, and those two boreholes are the things that we can recover 5 megalitres a day of water for supply. Just running through a few things, the chalk at Horton Kirby and Ainsford, we can get 11 megalitres a day as a peak. I think it's 6.8 as an annual average, but 11 as a peak. The treatment facilities that are at Horton Kirby allow for 16, not by accident. We left that in there with the intention of being able to treat this new ASR water stream along with the chalk water stream to have that done. So that's kind of basic of that. This is just hopefully something that makes sense in terms of a slice from Sevenoaks going all the way north to Horton Kirby. And you can see that here we've got the lower greensand aquifers, which in the Sevenoaks area has the Folkestone beds, a little kind of separating horizon called the Sandgate beds, and then underneath that's the Hythe beds. And that comprises 70 odd meters of lower greensand aquifer. As it heads north, it thins quite dramatically, such that we're only encountering this 15 meters of thickness here. But you can see that then as the River Darent flows to the north, it goes across the clay that's present just to the south of Otford. And as it leaves Otford, it starts to flow over the chalk and picks up base flow from the chalk all the way up to where it joins the Thames, much to the right of this picture. Here's kind of a construction of what the ASR boreholes look like. You've got a initial casing. There's a really frustrating delay with my pointer. So I'm trying not to use it as much. But the first section of casing in the ASR borehole goes down to about 190 meters, which is the base of the chalk. So we want to then drill that and isolate the chalk from anything else. Then we go through the tricky bit, which is drilling through the Gault clay. Clay's really quite a problematic thing to drill through. There's about 60, 70 meters of Gault clay. It's very important for ASR because it provides a really good seal, but it's also very critical that when you've drilled that, you can't go very far into the lower greensand aquifer, because if you do, you're going to spoil it, one, with the clay, and two, you're taking up the aquifer. So you want as much of the aquifer exposed. So as soon as you touch the lower greensand, you stop, get your casing in, and then grout that up so that it has this fully sealed throughout the chalk and the clay, and you've only got the interaction with the lower greensand. Here's what we talked about in terms of cycle tests. So very, very simply, you squirt some water in, which is recharge. I think the first one we did in 2008. So this was January 2008. We did 1 day of recharge in there, which is about half a megaliter that we put in. And then we did abstraction over about a 3-day period. So we abstracted a huge amount more than we'd recharged. And that's really baseline cycle to understand the properties of putting the water in, then take it out, and seeing the recovery of both the recharge water and then returning back to the native water. See that we were putting in, we're getting about 30 liters per second. That we are, when we're abstracting, it's about 30 liters a second. When we're recharging, we get up to 25, but eventually the sustainable rate of what we can recharge with various factors was about 1.5 megaliters a day, or 17 liters per second. So back in 2008, we did cycle 1, little squirt in, take all of it out. Cycle 2, a longer period of recharge, and then what looks shorter in duration, but is actually the same volume, because you're taking more out per second than you are putting in per second. And then cycle 3, a bigger one. So we had 16 days that we were going in, and then 8 days coming out. I think during this time, this was what we abstracted was about 90% of what we put in. And then the final one that we did in 2008 was 24 days of recharge going in, and then 11 days of abstraction. And all of that was to kind of demonstrate proof of concept, and more importantly, have a look at the water quality. So these are the water levels that are generated in the ASR borehole. Well, the blue's the ASR borehole, the green is the observation borehole that's 50 meters away. In terms of numbers, this is all relative to meters above ordnance datum. So ground level is at this point here. And interestingly, even though the aquifer is 250 meters deep, the water level is about ground level. It kind of fluctuates slightly above and below. Certainly at ASR 3, further to the south, it is an artesian hole about 1 meters above the headworks that we've got there. So we kind of have this generation of pressures when we're recharging in. So 60 meters above the headworks is where that pressure rises to. When we're abstracting, then it's down 80 meters here. Eventually we were getting to 90 meters of drawdown. So it's just illustrating you're recharging the water in, you're generating pressures that are 60, 70 meters above the headworks, which is about 5 bar. So we're really quite unusual headworks design to make sure it's not spraying out water everywhere. This is really just reflecting what I've talked about with the cycling and what happened with the water levels throughout that. This is what a headworks looks like. So we've got coming from this side, we've got the recharge pipework. So that's connected to the mains with sufficient backflow prevention, because obviously we don't want any of the ASR water going directly into treatment, so into supply. So we've got backflow on that. This then recharges the borehole, and this is the headworks that from time to time leaked and caused me a lot of dampness. And then when we re-abstract, we're taking at the bottom of this pipe going down 140 meters is the abstraction pump that then pumps out and either pumps to the sewer or when we have confidence with the water, we can pump that to the river. Little bit of a story behind the water quality that we re-abstract from it. So at the very first cycle that we did, so there's a very small duration of putting water in, and then when you take it out, we took out, I think 1,000% of what we put in. But very quickly you can see, using a variety of different determinants, you use chloride, so that's not chlorine, it's a natural occurring anion that's present in groundwater. In chalk water, it's about 34 milligrams per litres, whereas in the natural lower green sand water, it's much lower at about 14. This is also reflected by conductivity. So chalk water, as we all know, is quite a hard, mineral-rich water. So the conductivity is about 600, whereas down in the lower green sand, it's much softer water with conductivities about 350, but which gives us a good, both of those elements are quite inert determinants. So this is really just illustrating the mixing that you can see. So this is all the chalk recharge water that we're then re-abstracting, goes through this kind of transition to then you've got the pure native water that's down there. By the end of cycle 4 in 2008, and this is only taking out 80%, but throughout the whole of that 80%, everything trended along the lines of it maintaining the recharge water quality, which is positive for us. What we didn't want to see is deterioration in that treated chalk water down there, mixing too much with the native water that would cause us water quality incidents. And that's just a schematic kind of showing the borehole on the right, and then the bubble of treated water, a mixing zone, and then you're into the native groundwater, all confined by the gold clay on top of it. Well, yeah, so that's just the words from that. Quite a complicated slide, but all it's trying to illustrate is that during these 4 different cycles we did, the red line is how much we take out, the blue stuff in the middle is what we've recharged in there. So during the first one, we took out a lot more than we put in. Then we took 100% of what we put in. Then we did 90% of what we put in, and then 80% of what we put in. At the beginning, we were, by the end, seeing natural water quality. So it's got high iron, it's got high nitrite, it's got magnesium, all above drinking water standards. It's also got the worrying signs of arsenic. We've got ammonium that are above Thames Water's internal alert. So this isn't good treatable water. Throughout this period of time, we got at the end of 80% of recovery, everything was below the Thames Water alert. Arsenic was about Thames Water alert. And the aquifer was conditioned. This word, which really means it's you're cleaning the aquifer, you're what water you put in remains there, and you can take it out without it changing significantly. So it means that we could then just add the chlorine to disinfect, and that would be ready for supply. That was always all very good in 2008. We returned in 2014-15 to drill the Farningham borehole, and then moved on from that, equipping them with the recharge facilities such that we were able to do pseudo operational scale cycle tests. Again, using both boreholes, we were able to get about 4 point something megaliters going into the aquifer, and then we're getting 5 megaliters out of the aquifer, and much lengthier cycles that we're putting in. So we repeated 2 cycles during 2016 and 2017. These are schematics showing that the kind of bubbles of, if you assume that there's no groundwater flow, there's no dispersion, lots of assumptions that you have to make, and all you're dealing with is just the porosity of the aquifer, then you can make these circles which estimate the red outer bit is the volume of water going into the boreholes, and then the blue is what we re-abstracted out of them. So 2 cycles that we did, and estimating these 130 meters, 139 meters radius, whereas previously we were only much smaller than that. So bigger scale testing. And then this, I'm going to skip to the next slide. These are all groundwater levels, and all it's going to say is that these ones which are very close to Horton Kirby ASR 1 at Horton Kirby show fluctuations of 20-30 meters when you're recharging, and then 40-50 meters when you're abstracting. So the aqua in the area, the close area of Horton Kirby is fluctuating by these significant quantities. As we get further away from it, Southern Water have lower greensand boreholes heavily confined, as do Southeast Water at Hartley. And we were monitoring the levels there. What you could see at this point is that there are fluctuations, and then recovery from the abstraction that we were doing, and then perhaps a sign that that is inflated recovery or response to recharge. It's a bit tricky to see the Southeast Water one, because I think they use the lower greensand, and therefore there's these fluctuations and offsets that we detected. A lot of this is, I think, the transducer moving rather than it being a real step, but the spikes up and down. The main point is there was a limited groundwater response at that point. Further to the south, where the main concern would be, because this, if we were generating differences in groundwater levels at this point, then this is the point where it's interacting with the River Darent. So the scheme really fails if we start detecting any fluctuations in the groundwater level here. What you'll see that in the various scales, you know, each of these is 20 meters. For this section, it's 10 meters. For here, the whole of that is 1 meter. And pretty much, I can't detect any response whatsoever to any of the operations that we're doing. If anything, that seems to recover whilst we're abstracting at this point. So it is very difficult to see, even in this level of detail, any impact at all. That slide really just summarizes it. The Horton Kirby clear local responses. As you go further out, further away into the aquifer, there's limited groundwater response. There certainly are impacts that are going on, but they are less than 10 meter responses. And then when you get to these observation boreholes that we've got down in here, close to where the Darent could be impacted by these operations, we're not seeing any response at all. In terms of water quality, bigger scale things, and we hadn't done much testing for quite a few years, but we were seeing different responses from the 2 different boreholes. So ASR 1's the blue line, and you could to 40-50% before you started seeing elements of mixing. Certainly not getting back to native water quality by the end, but seeing that there was a mixing zone developing. ASR 3, a bit more interesting, with this kind of undulating pattern of things, which we'd never experienced with ASR1 previously. One of the thoughts is that now that we've got two that are operating, when you're recharging, they're kind of they're fighting with groundwater flows, so you start moving your recharge bubble into different areas. Likewise, when you're re-abstracting, a similar sort of thing happens. The upshot is really that it is complex, but we're still not concerned that it is a showstopper of ASR. And as a summary to all of that type of thing, at the end of all of that, we've got nitrite in ASR1 above drinking water standard. Now, the ironic thing with that is that basically the nitrite is purely converted from dismiss that one. Converted from nitrate, and nitrate is present in the recharge water. So when it converts by reduction into nitrite, it becomes more of a problem. What would happen during treatment is that nitrite would return to nitrate and it would fall within drinking water standards. Ammonium is still present, but not particularly a concern. It's certainly below the drinking water standard. Manganese, likewise. The big win was that we saw arsenic levels that are definitely stabilized, and arsenic was one of those things that was a reaction from the aquifer. So it's not necessarily present in the native water, but it's present in the minerals that the aquifer has that we're recharging into. When we then went to look at the blending of these, because obviously we'd be using ASR1 and ASR3, really most of these would blend out, and it's only manganese that would remain above the Thames water alert. Then when that was blended with the chalk water at Horton Kirby, then all water qualities would be complying with drinking water standards. So that's really the end of where we are. This illustrates what the plan would be. Horton Kirby is very much a drought scheme. That there would be an element of operation that would be there to just keep and maintain these bubbles of water, such that we would do the recharge during winter, where surplus water can be proven and licensable, and then this water gets stored, and we would be re-abstracting for a couple of weeks per year during peak summer, just to make sure that the water quality is still there, the system's still working, etc. But if we then hit our design drought, so a drought that is meant to last 16 months, then these are the volumes of water that you'd need stored in there, and just kind of an indication of what that would look like on the ground, of these large bubbles of water stored and ready for abstraction during a drought. So that's the end of my ramblings about things. Just to say, in terms of the obvious question, so you did all of that previously, why haven't you continued delivering it? Steve can support me on this, but the upshot is that we've got a supply and demand equation that keeps fluctuating up and down, and we keep modeling it. And the way that water resource management planning goes is that there are a number of options that we have, and then you have to have various models which select which scheme comes on at which time. I'm dumbing that down because I am dumb, and it's about as much as I can understand for it. So at the moment, Horton Kirby, which I was getting excited about delivering in AMP7, that's been deferred at this stage. You may note, with eagle eyes in the draft water resource management plan, that delivery is now in 2050. I think there's been quite a few responses to the water resource management plan that have questioned that, and Thames Water are very much aware of those, and I'm hopeful that there could be changes to that, but they're still within this water resource option selection process where schemes. Now, my personal view is that ASR is a form of managed aquifer recharge. It is climate change resilient. It is something that we need to be showcasing and developing a scheme which is operational, ironing out as many of the bugs that will inevitably come when we deliver this very innovative scheme. And by delivering Horton Kirby, it gives us more confidence to other ASR and managed aquifer recharge schemes that exist within the plan, that if we've got one that we can operate and we can make work properly, then we'll have more confidence about including those. Any questions?
Brilliant.
Jamie, I just think it's maybe worth adding in that context about your last point on the timing, where we are with Southfleet and Greenhithe in the context of the WRMP. So that's planned for delivery at 2031. So as Jamie's explained, the modelling behind the WRMP takes into account all the options there and comes up with initially a least cost plan, but then a plan that also takes into account things such as biodiversity, net gain, etc., etc. And the Southfleet and Greenhithe scheme, which is based on taking more of the water, as Jamie described, that we've exploited using the bean source, and increasing that amount of abstraction to take water that's lost currently through dewatering at Blue Water Park and would otherwise go out to the estuary. So that scheme's brought forward to 2031. But when I spoke to my manager and said, you know, we're going to be talking to you guys about that, what's the take on Horton Kirby ASR in relation to timing and possibly coming forward? And he said, yeah, our WRMP is heavily based on quite a strong demand management portfolio, including leakage reduction, metering and water efficiency. And we are aware that that's got quite a lot of uncertainty with what will be realised through the delivery of the demand management programme. And so the Horton Kirby ASR scheme is a scheme that we have that could be brought forward if needed, if we are not closing the supply demand gap through the demand management programme. So it could come forward from 2050 to fill that gap is basically our plan at the moment.
Brilliant. Okay, thanks for that.
Can I just quickly thank Jamie for all of that? We're making enormous strides in understanding what goes on. This native water, Jamie, that you were talking about at the beginning in the lower greensand, tell us a bit more about the transport of that. I mean, is that the same greensand aquifer we have in Westerham, which and beyond, further east? And if so, what sort of distance does this stuff travel? And you might throw in, are there better places than the one you've chosen so far, because the greensand is fairly thin there?
So it's a bit of a catch-22. We could do an ASR scheme very close to Sevenoaks. Unfortunately, that bit of monitoring that we did, where we're monitoring the groundwater level, I'll guarantee that it wouldn't be an environmental solution, because you'd be abstracting and recharging at a point close to Sevenoaks, and you'd be impacting the areas of the aquifer that are feeding the Darent at the moment. So in terms of better areas, you want to be sufficiently far away from the unconfined elements of the aquifer, such that all of your jiggery-pokery with putting the water in and out doesn't have a knock-on effect down at the point of environmental interaction with the river and the aquifer. So that answers the point of new places. A similar setting for the Horton Kirby ASR scheme exists all the way across the south of London. Unfortunately, the knowledge of these things is pretty limited. So it would require this kind of 10, 15 years of investigation that we've done at Horton Kirby to be repeated elsewhere. There are certain examples. We've got one ASR scheme which is in the plan for Addington. So in the kind of Croydon, South Croydon area. Part of the Darent, but that's another very similar example. In terms of the water, it's a bit before your time. Some of the water at Horton Kirby is about 8,000 years old. So it is very much the same water that we're seeing in the
Stuart
unconfined
remembers that.
areas. Yeah, I was about
I'll
bit
crack
before
it
his
before
time.
anyone else does.
Yeah. So it flows very, very slowly to the north. Basically, there's no natural discharge point. So groundwater's really good if it's got recharge and rain that falls at one point, and then flows to a point where it discharges into a river. So the kind of chalk is ideal because it's recharged across the North Downs and then heads to the River Thames, River Darent, where it discharges there, and it develops as an aquifer, so you get quite high flow rates. When we're dealing with the lower greensand, it's very different. It doesn't naturally discharge. That there's certain theories that it heads out under the North Sea to the kind of estuarine Thames and may start seeping that way. There might be some element of to the further to the north that there might be a slow creep that goes through the Gault clay into the chalk, but basically there's no quick way of it flowing. So it's quite a stagnated water within an aquifer that's full of minerals, which is why we see the water quality full of iron, etc.
That's fantastic. Jamie, can you still hear me? I've lost my picture.
I can hear you very clearly.
Yes, thank you. A new friend of ours, fairly new, is a gentleman who's here today called Chris Johns, who is a retired petroleum engineer. And three of us must meet up. He's got experience in a parallel universe.
Yeah.
I think between us, all these WRMP things where we're invited to comment, I find very, very difficult because we do not have enough background information. You're now beginning to help us to understand why changing the deadlines and the urgency of various things might well be exactly what we need to influence. Because if we're watching climate change across Europe, across the planet, and there's enormous gobs of water that come down in 3 days, and then you have nothing for 3 months maybe, then we need to plan for this. And if it takes 10 or 15 years, we got to start today, not in some other time. So I'll shut up. I will sign off, Chris, and sign in again to try to get my picture back. Thanks, Jamie.
Cheers, Stuart.
All right, Stuart. Bear with me, Brian. Daniel has had his hand up very patiently for a long time. So, Daniel, can I just come to you quickly?
Yes, thank you, Chris, and thanks, Jamie. Really an interesting presentation about the ASR, and it was particularly interesting from my point of view, from my work delivery as a catchment intensive farming officer, on some of the challenges you're facing there with the nitrate levels well exceeding the DWRP. So are Thames Water actively pursuing any schemes with landowners to try and mitigate the levels of nitrates they're seeing entering the boreholes in the ASR aquifers?
So a very quick response to that: the Horton Kirby chalk abstraction, they don't really have a nitrate sensitive designation, whereas our South Fleet source and a lot of the Bean well fields, so the new replacement well field that we constructed, they do have certain boreholes which are exceeding the nitrate PCV, the permitted level. And therefore they have got a catchment partnership initiative where they're liaising with farmers and trying to do that. I don't know whether that was delivered in AMP7 or whether that's proposed for AMP8. There's one of my colleagues, Joe Clint, is very much behind that and is in charge of the Thames water catchment management associated with nitrate and fertilizers.
Oh, sure. It's it's kind of obviously Darent Cray is one of my catchments I operate in, so it might be really useful to maybe link up with your colleague there.
Yeah. So if you you'll have seen my email in the circulation, I think. If not, then someone can send it to you, and then I can provide Joe's details, and she can speak a lot more eloquently about it.
Okay, great.
I do know, just to add to that, Jamie, that Joe recently was involved in an event where she was talking to landowners about the sorts of things that she was doing, Daniel, because she asked
that promo event. I unfortunately couldn't attend it.
Okay.
It might have been. They had some attendance from farmers and other folk. I think it might be that, but don't quote me for it.
Okay. But anyway, yeah, we can certainly put you in touch with Joe for an update and what she's doing.
Brilliant. Thanks, Steve. Steve Barrow, you got your hand up. Oh, sorry, Brian. You were next, weren't you? I do apologise. Brian and then Steve.
It's really just a very simple. Can you hear me?
Yeah.
Yep.
It's really just a very simple question. What I can't see is the scale of what's would be achieved from Horton Kirby. We talk about megalitres, etc. What are we talking about? A week's supply for a village, or what? What sort of yield that could?
So my simple view.
Resource is it? I suppose is what I'm saying at that scale.
It used to be my go-to response that a megalitre per day was about serving 5,000 to 6,000 people per day. I think we're now trying to reduce the per capita consumption, so I think it might be more than that now. So we might be getting to 7,000 people provided by a megalitre of water, which then, if you've got 5 of those, that's 30,000 people, 35,000 people
for one day.
Yeah, for each day that it's going. So as a typical thing.
And those bubbles,
ballpark figures.
Those bubbles we were talking about were 11 megalitres, was it? Or what was the capacity?
So I think what you might be getting confused with there was that the chalk peak abstraction from Horton Kirby is 11 megalitres a day. Right. So that's existing. The ASR scheme is the design is an additional 5. So it's ASR would give you 5. In the scheme of things, it is quite small compared to the whole water resource zone capability. You know, London is 2,000 megalitres a day, give or take. So it's not quite drop in the ocean, but it's a bit of a sprinkle. And my view is that it's very useful for peak supply problems, and not just having that peak supply, but also being able to deliver during peak supply without the environmental impact.
Right. Okay. Yep.
Jamie, the general public feeling is that we need to build more reservoirs, and we haven't built reservoirs for 50 years, and they take so much planning permission and all the other stuff that goes with it that is real an uphill fight. Once you get planning permission, it still takes another 10 years. The option of using something underground, which, if you like, nature has provided, seems to be a blindingly obvious alternative because the water won't evaporate. But the problem is obviously that, as you say, some of it's been there 8,000 years. It may be replenished, it may be not. Maybe there's enough of it we don't need to worry about. We won't be here in the next 8,000 years. Blah, blah, blah. But I think ASR, just intuitively to me, seems to be top of the list of things to be getting on with.
So, Stuart, you must be a groundwater specialist, because these are the sort of things that I get carried away with. We do have to put it into the context of that size that I was alluding to. So, for the whole of the Darent, I don't think we could get another ASR scheme in there, because the interference would then start being more problematic. Horton Kirby is about the right sort of area to be constructing this ASR scheme, and then that will cover the Darent, because anything further to the south, as I talked about, may start causing environmental problems. Anything further to the north, the aquifer thins even more, and I think by the River Thames that it's disappeared. It's not there. So I definitely think there is potential to have more. But it's, you know, across the whole of the south of London, we're probably really getting carried away. You're only talking about another 3, 4 schemes that you could develop in this manner, and that's going way off piece from the Thames Water view, but it gives you an indication of potentially, by throwing everything at this, we might end up with 25 megalitres from that. The reservoirs that you're talking about, you know, there's another order of magnitude on that. So it's economies of scale, whilst not giving up on something that I quite like, the whole concept of ASR.
Yeah, it's worth adding, Jamie, isn't it? If you look at the whole of our supply area, Stuart, we have done a lot to try and exploit this sort of option, and we've got the North London Artificial Recharge Scheme, which would be great if you could find another location to do something similar, but there just isn't one, as Jamie's outlined. And you know, NLARS, as we call it, is a big scheme that can get up to 150 megalitres a day. So we're doing quite a bit already, and there's nowhere else in the country with anything quite like that.
Brilliant. Thanks, Steve. I'm going to come to you, Steve Barrow, in 1 second. I just want to ask one quick question myself, which might help me sort of understand, I guess, why maybe this has been delayed. Is there a reason why this has been delayed in terms of cost? So you're pumping water into the ground and then you're abstracting it. Perhaps it's under pressure and so it just comes out naturally. But is the operation of this scheme, like, you know, I don't know, say you had, you know, what's the cost of operation of a scheme like this? Is it obviously like a chalk borehole, the water just comes up, so I'm assuming that's pretty low cost. You know, a desalination plant is using loads of energy and the water that you're getting out of it is very high cost. Where does this sit on that sort of scale of?
So maybe Jamie can answer that specific cost question in a sec, Chris, but in terms of the mechanism for choosing the scheme, it's done through the model that we use to come up with our WRMP. So it takes into account all of the schemes we've got and their costs, both CapEx and OpEx, in relation to the scale that they can provide and the scale that we need to meet. And so there are other schemes that are coming in before them because of the scale and cost. So we've got some new schemes that would come in before. If you really wanted more detailed chapter and verse on that, we'd have to get somebody called Peter Blair to come and talk to you. But I think Jamie could maybe answer the question on the specific costs of operating Horton Kirby ASR better than me. Jamie.
Yeah. So unfortunately, the legislation, well, unfortunately and fortunately, in order for us to recharge it, we need potable water. And therefore, it's basically the cost of producing that chalk treated water is the baseline of where we go things. Then we've got to recharge it, which we try to maximize using the mains pressure, the natural mains pressure that exists. But we do need to boost it, so there's an additional cost to that. And then when we take that water back out again, so we are pumping it, and even though when you recharge the water level is 70 meters above ground, when we're abstracting, it's 140 meters below ground. So we're certainly having to lift it. We are pumping it up. So there's a significant cost there. The details of it, as a broad brush, I'd say it's at least double a conventional chalk abstraction. The treatment is just simple chalk treatment. You know, we're just disinfecting that water, and that's when it will stack up. If we had to do anything more complicated with it, then it really tips the balance of it. But it is a costly scheme to do. The kind of designs that have gone on during this period, AMP period, have been really to get the pipelines to get that raw water to the Horton Kirby treatment works, and then upgrade more about the control facilities at the treatment plant to be able to bring in this different water quality, treat it, and then put it in supply with confidence that it wouldn't have any adverse effects. But I think in general, at least double.
Okay, that's really interesting. I'm just going to come to Steve Barrett in 2 seconds. It just seems that you've almost built a reservoir and you're not using it until 2050. If I can just be quite candid, and that just doesn't make sense, I think, to me and probably other people on this call as well. So that is a bit of a head scratcher. I was just trying to work out why that might be.
Steve?
Well, I can't really add any more than the reasons that we've explained already, Chris. There's quite a long way to go to get Horton Kirby ASR to be functioning with putting water into supply. So it's the cost in doing that compared to the cost for the other options that mean that it's coming out when it does.
Okay, Steve, you've had your hand up very, very patiently, so apologies. And
no problem. Well, I've now got 2 questions. In that, first one was fairly straightforward. In that, how much extra do you inject compared to how much you abstract to get that sort of red fringe around the outside as a sort of safety kind of thing? And the second question was, is SLARS something you're still exploring in terms of abstracting from the confined chalk under South London? I know it's sort of been on the books for a while.
what is SLARS? Can you just...
South London Artificial Recharge Scheme. So the thing that Steve talked about in terms of the North, which has been operational since 95 and trials were going on in the 50s about recharge just using the chalk. So it's confined chalk, putting water in, taking it out. It's very different to ASR in that it naturally recharges and the water that's there already is easily treatable. So ASR is taking an aquifer that's not got good water quality, and you put your treated water in there and you keep it there and you take that back out. NLARS is a scheme where actually we could just be abstracting from the chalk, which is in effect what we're doing. Having done that during drought, then naturally the water levels will recover, and there's no interaction with the environment. But as part of the license, you have to have a state of storage, so a level of aquifer fullness that goes on. So that's clearly what happens with North London Artificial Recharge, NLARS, but SLARS is a scheme that we started developing in 2003, something like that, and various trials went into it. The conclusions were that the geology isn't quite as simple, and the concept doesn't work particularly as it does in NLARS. For NLARS, basically the basin's a bigger basin at that point and more simple geology. In SLARS territory, so from kind of Deptford area up the Ravensbourne and around those sort of areas, a whole variety of boreholes. When you start recharging, there are various consequences and water quality concerns and various things. So the upshot for SLARS is that they're still in the plan, Steve, under a variety of different guises and different magnitudes that could be called upon. So it's kind of like triggering which one will be selected at what point. That hopefully answers the SLARS question. I'm now trying to remember what the proper question was for me.
It was how much extra do you need to inject versus how much you abstract?
Okay, yes, yeah, that was easy and I smiled at it. Who knows?
At the moment, yeah. What was that?
Daniel, are you trying to say something?
Go on, Jamie.
You can see throughout the cycle testing that we've kind of gone from 100% then to the last one being 80%. It will end up being trial and error, and it will the trial and error will probably relate to operational experience when we get to that point, but nominally between 80% and 90%. It will end up being, you've got this big bubble of water that's stored there, and isn't doing much, and then on a yearly basis, you would be looking at squirting a certain amount in and then taking a little bit out, probably nowhere near that. But then it's difficult to come up with one answer, because the scheme really is for use in drought conditions. But you can't be as naive as to wait for the drought to happen and then expect all of that bubble to come out and not have any problems. So we need to be on top of getting the bubble established, and then on an annual basis, still being useful for peak demand periods, but really quite limited, and then oscillating it around a little bit whilst trying to monitor from the various other observation boreholes to check on water quality.
Brilliant. Thanks, Jamie. Okay, any other questions for Jamie or Steve on ASR? No, right, I'm going to stop the recording.